Okay, share my screen. Okay, so I had sent these three examples as practice exercise. I had sent these three examples for you to practice your skill on coming up with loop invariants in by email. I hope you had a chance to review it and take a crack at coming up with a loop invariance. I want to discuss that briefly, and also discuss the point about how a loop invariant can be considered as an as over approximating the behavior of a loop. Okay, so first let me see. I mean, if any of you, okay, this is the factorial. The first two are factorial examples, which we discussed last time, and the first one computes it by setting the variable. It computes n factorial. The first one computes it by setting x to the number for which factorial is meant to be computed, and then counts it down. Whereas the second example initialize the variable x to 1 and increments it up till it accumulates the multiplication. So let me see if you, if let me ask you if anybody did take a crack at doing it. So if so, then I'll go by. So the question is, what would serve as an adequate loop invariant, a loop, which candidate predicate could serve as a loop invariant that is able to prove the given post condition at the location L. Okay. So let me go by from the list of people who are here. I don't know if there are some more people that have joined. Let me see, so that I'll keep a list. So Deep Pro has also joined. Okay, so Vardhan, have you? I know you were not there in the last class. Did you get a chance? Okay, so then I'll move on. Lucky,
I think we discussed this in the last class. The answer was probably n factorial equals to x factorial into fact or something.
well, why don't you make your answer
Hello.
precise?
Uh,
I know we had
loop
discussed, so it should make,
invariant.
if you were there in the last class, it should make your life easier to give an answer.
So, n factorial equals to x factorial into fact.
Yeah. Okay, so what he's saying is, Lucky is fact times what is in fact is the partial result times x factorial is equal to n factorial. Correct? Is that what you meant? Yeah.
Yes, yes, sir.
Yeah. Okay, this will work in this case because what you have is there is some more computation to be done, which is the x factorial. Fact has the partial computation, and this will work in this case. So the point I was making last time was, when there are in general in a lot of cases one idea to a hint, a tip to think about to use to construct suitable loop invariant is to use this. You have to figure out something that is preserved across all iterations. That's what the loop invariant predicate captures. And sometimes it is useful to think along these lines. It has to be some predicate expressing a relationship between three entities. The computation that has been done till now, and the computation to be yet to be done in future iterations, which could be related to what you need to accomplish as a result, which is captured in the post condition. Okay, so thank you, Lucky. Okay, let me move on to the next example. Uh, so we briefly discussed it here, this one as well. So let me go to Harsh.
Actually, I was not present in the last class, so I don't have an idea about
Yeah,
this.
but I think we record the class lectures, and you had I hope everyone, since we record the lectures, I would generally expect that you would be diligent enough to go through the recording, okay? And, have at least some information, okay? I'd be happy if you could follow through with that in the future, okay? Thank you. So let me move on. Um, Sai Shashank,
Yeah. So I think
you are
in
in the same
the
boat as Harsh because you were not there
no,
in the
but
last class.
I was not there, but I have a have an
Okay,
answer
good.
for
Yeah.
this.
What would that be?
We're starting from one, so it would be fact
So
equals
what is there in
n
fact?
minus x factorial.
Okay,
Yeah.
say it again.
So fact equals n minus x factorial.
Yeah, but in this fact is equal to
N minus x factorial.
what fact has is actually you're multiplying all the way from 1 to x at any point. Is
Right.
it any point in the iteration? So fact itself will be
You'll be x minus one
you're
factorial. Yeah.
exactly right. Okay, so that one, x minus 1 factorial. Sorry. Yeah.
Yeah.
Good. Yeah, so that's quite good because it is x minus one because after you multiply the x, you increment the x plus one before by the time you get to the point indicated by location L, and that's why it will be x minus one factorial. Uh, but is this which is actually true? I mean, which is inductive at L, but is this uh, safe or adequate to?
I guess we need a condition for termination,
Yes, yes, good.
which
Yes.
would be
Uh,
x at n plus 1. So it should be less than or equal to n.
that's exactly right. Very good. Okay. So you also need the condition that x is less than or equal to n plus 1. Okay. So at this point, since you enter the loop, even when x is equal to n, so x is less than or equal to n plus 1 is what is true. And therefore, when the loop exit condition holds good, you with these two information captured in these two conditions, you can conclude that fact is equal to in factorial. So this is a very good illustration of sometimes you need to strengthen you may find a predicate which is inductive, but may not be strong enough for you to prove the post condition, and you may need to strengthen it by looking at what additional information you need to strengthen it by looking at the loop condition or some other information. Okay, so any questions there? Okay, so who had a chance to look at example 3? Deepro? Deepro, are you there? Okay, I thought he was there on the thing, so maybe he's joined the meeting but wants to remain silent. Okay, so let me then go to Aritra.
Hello, sir. Yeah.
Firstly, let me first explain, okay, the notion of an invariant, okay, independent of a loop invariant. An invariant is any condition that holds good for the program. I mean, it's usually associated. Invariant associated at a particular location L is any condition that holds every time the control uh, is at that location. Okay, so so in this case is z plus 1 whole squared. See, z plus 1 whole squared is an invariant, okay? In the way that z is modified by the loop, z plus 1 whole squared indeed holds good every time control is at the point indicated by location L. Because the first time you get z is 0, so z plus 1 whole squared is and x is 1 holds good. And the way x and z are incremented, this holds good every time in each after you execute every time after an iteration. Okay, but it is not a loop invariant, because a loop invariant also needs to be inductive. Okay, and that's what the thing is. So z plus 1 whole squared, if you assume inductiveness check can be done by assuming starting with in a state in which the condition x is equal to z plus 1 whole squared is satisfied at L, you enter the loop, assuming the loop, in this case, this is a non-terminating loop. So you always enter the loop, and after you execute one iteration, you should check if x is equal to z plus 1 whole squared holds good. Okay. So yeah, now I'll go back to Aritra. Okay.
Yes,
Now
sir.
you could
Yeah.
answer. Is it inductive?
The previous one you said it's not inductive, like it's an
Okay.
invariant, but it's not inductive invariant, inductive loop invariant.
Yeah. So then the question is, okay, what can you strengthen it by to make it inductive? Okay.
Okay.
Yeah. So at least you answered the first two parts. That is good. Okay. And that kind of indicates. So I'll give you an idea. I mean, if you have an answer, you can let me know, but I can give the rest some hint. Okay.
It will help if you can give me hints. Actually, I
Yeah,
tried this,
why do you
but
think that's good? So, here it's also help you make you think. So, you see, and this happens oftentimes. It actually did in the example that we discussed in the last class, the even example. Okay, So there were two variables there. So usually here, what is not captured by the loop invariant is in how y changes, okay?
Okay.
And that is also important because the way x changes, x changes to x is dependent on y, okay? You see?
Yeah.
And, so therefore, you need a relationship in order to, the relationship between, the intended relationship between x and z plus 1 whole squared, which is being captured the loop invariant, is somehow dependent on how x changes, which itself is dependent on y. Okay. And therefore, you need to also, the loop invariant has to have a part which it captures the relationship between y and x. Okay.
So yeah. So we can actually find a relationship between y and z. So basically y is equal to 2z plus 1. Then we can replace z with y to get the relationship between x and y.
Yeah, something, yes, that would be a way to do. And that relationship in this case is exactly y is equal to, I think, 2x plus 1.
I equal to 2z plus 1.
Yeah, y is equal to 2z plus 1,
2z
right?
plus 1. Yeah. Hmm.
And that's, with that, it'll capture, if you strengthen this, then this whole thing will be inductive. Inductive as well as an invariant because it'll hold good the first time you're there at L, and this will be true. Okay, this is something that you need to be aware of. Okay, just because you can come up with if it's not inductive, you need to think, oh, let me see if there is some other relationship between other, that is missing in the loop invariant that you need to add as an additional condition. That's what I mean when I say you needed to strengthen your initial, predicate here to make it initial guess to make it inductive. Okay, good. So thank you, Ritra. Okay, one more. Yeah. So any questions? Okay. So if none, then I also mentioned this briefly last time, but let me illustrate. There is one other person who's joined. I want to, Pranika is here as well. Good. Okay. And I want to re-emphasize that. So a loop invariant is considered as an over approximation of the behavior of loop. Okay. So I'm introducing here explicitly for the first time this notion of over approximation. We will revisit this more in the future. But okay, this is the our original program, the program that I used to illustrate loop invariant in the last class. Okay, here x and I are initialized to 0, and x is incremented by 2 every time. X is incremented by 2 and I by 1 every time you go around the loop. Okay, and so if you needed to prove that x is equal to, the post condition is x is equal to 20. We discussed various candidates for loop invariance. For example, even x itself is an inductive loop invariant, and I less than or equal to 10 separately is also an inductive loop invariant, and its conjunction is also a loop invariant. Okay, so a loop invariant, as the way it is defined, it includes all possible values that the program variables can take during all iterations of the loop. The key word is includes. Okay, so in some sense you can replace the entire loop by the loop invariant. And that's what I'm doing here. The program I'm showing here is the same program as before, except that there the loop, the while loop, is replaced by an assumption which exactly characterizes the condition defined by the loop invariant, which in this case is even x and I less than or equal to 10. So I start, you see, the effect of these two statements here is that I set x and I after the initialization to be some arbitrary value, and then assume that it can take any value that for which this loop invariant condition here holds, which means it has to be even of x and I less than or equal to 10. Okay, and this is what when you check the post condition using the loop invariant, it is this exactly captures how you could one way to check the post condition. So you assume that, and then you assume that the loop exit condition holds good, and then you check if your post condition, which is described in the assert, holds good. So this loop invariant here, in this case, it certainly includes all the variables. Okay, I mean all the values that x and I can take across all, but it also adds something more. Okay, that is not feasible by the program. For example, even if x and I less than or equal to permits x to be anything, okay, as long as it is even. But you know that x, there is a bound on the x. I mean, on the value of the x that the program execution can actually take. I mean, it can make x program can make x take. So it is in that sense when I say the loop invariant is an over approximation of the behavior, it does include all the behavior of the original program, but it can include something more beyond that, which in this case, x, it doesn't bound the value of x, although it does bound the value of I. Okay, so and that's the reason when you replace the loop body with this with this loop invariant, you are not able to prove x is equal to 20. Okay, because for that you need also some additional information in your loop invariant regarding the bound of x. Okay, which is x less than or equal to 20. Okay, so that's why when you use this loop invariant, you will, your post condition check will fail. That doesn't mean, okay, that your program violates the post condition. It could also mean that your loop invariant is need to be strengthened. Okay, so it's in that sense that the loop invariant you can always replace a legitimate, a valid loop you can replace a loop with a loop invariant, which is with a valid loop invariant. And what you get there will be an over approximated program. But if the over approximated loop invariant is strong enough to prove your post property, then you still are able to prove the program correct. If not, if it fails, then you have to look for ways to strengthen the loop invariant. So it's in that sense this you can a loop invariant is considered as an over approximation. Okay, that's the point I wanted to make. Any questions? Okay, good. That's all I wanted to convey. Okay, and this week's tutorial, I'm planning to have Shaurya and Avi discuss more about not only loop invariance but also in general about OR logic and PyTorch and so on. So I'll announce the topic for the tutorial this week later in an email. If there is no more questions, then I will stop sharing, pass the baton to Diganta.
Yeah. Okay.
Go ahead, Diganta.
Shall I? Yeah, I'll just start screen sharing. Let's see if my screen is visible. Is this visible?
Yes.
Yeah, yeah.
Okay, yeah. So this is going to be a fairly quick introduction on for recurrent neural networks. So yeah, so I'll introduce what they are from a point of view of okay, what are the various pieces of it, what are the moving parts, and also talk a little bit about why they are what kind of problems they're being used, how to train them, some of the issues that happen when you try to train them, and that'll to a certain extent motivate why they are not the part of the recent revolution in LLMs. LLMs are very different from recursive neural networks, and one of the reasons is that the motivations for the LLM architecture is comes from the limitations of the RNN architecture, right? So I'll talk about some of those points, and also I'll talk about the Professor Srivas has already talked about program invariance, and in general, this concept of using an inductive invariant to prove something. And I'll say how a little bit about what is recursive neural networks, the state space, and what an invariant there can look like at a very high level. I'm not going to spoil anything about the paper that is actually going to be discussed next week.
Yeah, reinforcement is
Yeah,
always good, even if there's overlap.
yeah, of course, yeah, definitely. Okay, so with that, I guess I'll just start. So what is what are RNNs, right? So let's imagine that we have some problem where we have so far we've been looking at neural networks where the kind of domain that we have been looking at is Rn, and then we want the output in Rm, right? So just to recall, this could have been an image where each pixel is somehow mapped to a component of a particular component of a vector, right? So you have this long vector, which is just a list of pixel values. Let's say the pixel values are between 0 to 1 or something like that. And then therefore this vector really encodes what an image has and is just something that sits inside this Rn, right? And then your neural network is supposed to give me a distribution of scores as to what it thinks, what it thinks the likelihood of this image being of a particular class, right? So the classes could be something like cat, dog, etc., right? And this is again a vector, so that again sits inside Rm. So far the networks that we have been looking at are purely of this particular form, where they take something that is inside Rn and then they output something that is inside Rm, right? However, there is a large class of problems where this is just not the case, right? So imagine if we want a neural network to be able to read some text, right? Let's say something like I am something like this, right? So this is a sequence. There is really no lossless way of taking this text and encoding it as a vector inside Rn, right? Because we don't have an upper bound on the length of the text, right? So this is a sequence, and a sequence, generally speaking, can be of arbitrary length, right? So in some sense, if we want neural networks to now take words from some language and then output some word that will again be in some other language, let's say, if I want a neural network to be able to do something like this, the kind of architectures that we've been looking at fundamentally won't work, simply because they have fixed number of input neurons, right? So you can't even pass a word of arbitrary length, like it won't fit over here. If your words are of bounded length, maybe, right? But then your network is going to be very wide with respect to the amount of or the length of your word, right? So like if I want a reasonable network for text classification, let's say that I want, given some text, I want to understand whether this is a happy text or a sad text. It could be paragraphs long. So my bound on the length of my sequence, or I'm calling it word, but like when I say word, I mean a sentence or something bigger, right? So I'm saying word in the formal language sense here. But in any case, the bound on the length of my sequence would have to be very big to accommodate all of the kinds of data that I want to classify. And then the whole network itself would have to be that wide, right? So now you've got this huge network. So this is something that is kind of, one can imagine that this is going to be something that is difficult, right? So what do we do, right? How do we solve this problem? Well, what do you do in a normal setting, in a program setting, right? So if you want a program that is going to manipulate strings, right? So some program that is going to take some string, and it's going to do something inside. Typically you don't declare a large number of input variables for each element of your string. So you don't do something like card a1 equal to s0, a2 equal to s1, and so on, right? So nobody does something like that. What we typically do is instead we write some kind of a loop, right? So we'll do something like
Yeah, Diganta,
yeah,
you
yeah.
have laptop battery low.
I see. Yeah,
Warning.
I think I forgot to turn this plug on. I see. It seems that this particular plug is not working here. Yeah, now we're good.
Okay.
Okay, so thanks for letting me know that I had missed it. But in any case, we'll have some kind of a while loop, right? So we'll have while loop where let's say that we have some c is not equal to some null character or whatever, right? And then c is equal to s0, and then we do c some processing with C, and then we do C++. So some kind of a loop of this nature, right? Typically, that's how we write a program. So the natural kind of first step to solve our problem of how do we get a neural network to work with sequences is to sort of take this kind of an architecture and convert it into a neural network, right? So in some sense, what we're looking for is a neural network that looks something like this, where you take your sequences of whatever, pass it to the neural network, and the neural network itself is going to loop in some sense, right? And then by doing this kind of loop, it's going to now output some vector, like or some output value, right? So this is a fairly natural thought, but how do we, like, what is it precisely that we need to do, right? um Okay, so before we go to that, I mean, I just want to say maybe that this is something that is, it's kind of, I mean, I think this is perhaps very clear, but given the modern prevalence of LLMs, but being able to process sequences does give us a lot. It immediately enables things like text, audio, and so on and so forth. So it immediately enables things like a chatbot from, you can now write a chatbot as a like neural network, or you can have a text completion engine, and we know that basically language models are just completion engines, right? At a very high level, and so on and so forth, right? So yeah, so the motivation is there, and the way that we want to do is we want to somehow think of a neural network that runs a loop. So what do we need to run a loop? Typically, in any program that we have a loop, we would have some variables that kind of store a state, right? So let's again imagine that we have a program. um, we have some kind of a while loop, some condition here, and of course I'm going, I'm consuming character by character. So like, let me maybe think of it as a for loop or whatever, right? So for some character c in some string s, I'm doing something, right? But typically in any kind of normal programs, what you would have is you would have some kind of variables, um, and then when you do something with c, you manipulate these variables and store some kind of a state in them, right? And then you repeat this loop again, and when you repeat this loop again, the state that you have stored in these variables come into play. So let's imagine that if we want, let's say something like I want a simple search, right? I just want to look for the word foo, correct? So I can store the state that whether I've seen an F so far, right? So that I can store in some Boolean variable. And now that I've seen the first F, then I can store, okay, now have I seen an O that I can store in another Boolean variable, B2, let's say. Right. Okay. So now we've seen both of these two things, but let's say that instead of O, this was an X, then we again reset B1 and B2. So we have not matched it so far, right? So these kinds of things we can do. And this is not nothing, I mean, very difficult in the sense that you probably have done a lot of this when you've written programs that take in sequences and output sequences, right? But basically what we need is we need this kind of a looping structure, and this looping structure should maintain some kind of a state. So far this is a fairly natural concept, right? But how do we make a neural network architecture, make a neural network actually do something like this, right? So RNNs are basically just the natural way of interpreting or creating an architecture that will do this, right? So what we do, okay, so what we do is we have a network, and this network is going to take in some, so it's going to be a loop, right? So it's going to take in a few things. So let's imagine running one iteration of the loop as a neural network, right? So it's going to take in, let's say, an element of my sequence. So let me just call it xi, right? So let's say that somehow goes to these few neurons of the network. It's going to take in the previous values of the state, whatever the state is, and that's going to somehow go to these neurons, whatever that may mean. And then this is going to be a whole neural network with as many layers as you want. And then finally the output is going to be again some output yi, which is, let's say, the output element of the output sequence. But also I'm going to say what the next value of my state is, right? So this is going to give me si as well. So this is essentially what we want, right? And this, notice here that there is this kind of a loop, right? So this si will again loop back into these things for the next iteration, right? So this is a direct translation of what we have when we have a program where I have these ABCs, and instead of, so all of these operations involving C's, A's, and B's and whatever, these operations, instead of them being actual statements that I'm writing, this is now instead some neural network, right? And this neural network is again just going to look at whatever A, B, C state variables was before, and it's going to consume whatever let's say I call this X. So it's going to consume whatever X it has, and then ultimately it's going to produce whatever Y to be, let's say, printed out or outputted or whatever. And it's now going to give new values to ABC, right? And this is basically what an RNN is at a high level. Okay. Right. So how do we interpret how RNNs operate, right? So in this instance, what you'll have is, let's say that I've gotten some sequence x0, x1, x2, right? I can think of the RNN as doing something like this. So it'll, in the first iteration, it'll look at x0, and let's say that I've fixed some initial state s0, right? So this is basically the init part of my variables ABC before the loop happens. So it'll look at s0 and it'll look at s0, and then both of these two things are going to be passed into some network. And then this network is going to produce the next value of S and the output Y0. Right? So this next value of S is now going to be passed into the network again, and it's look at X1, and it will produce Y1 and something else, right? So when you are going to run this RNN, this is essentially what is going to happen in your as a block diagram or kind of a schematic, right? Now notice here that this can actually process um, uh, arbitrarily long sequences, right? So there is no limit on the number of elements in my sequence. There is no, you know, I don't need to have some upper bound on how long of a sentence that I can process. I can actually use this kind of an architecture to process any kind of sentence, right? So yeah, so this is kind of the idea of the RNN. and this S naught is going to act exactly like the kind of these Boolean flags B1, B2, and so on and so forth in the when we are matching against whether we have seen some part of a word or not, and when we want to search a word. So in some sense, they're going to store some amount of context, and yeah, so this context can take a look at whatever we have shown so far, and decide what is good output to produce at this point, right?
Yeah, I just want to make one observation or comment. Okay. There, and you said, yes, you said that, yeah, storing, having some memory allows you to process arbitrarily long. Okay, which is certainly true. Okay. But I guess since you're bounded by, I mean, you can only store bounded information. It puts some
Right.
limit on the accuracy with which you could process this arbitrarily long thing. Correct? So,
Yes,
yeah.
yes, absolutely. So that is actually a very good point. So I was thinking of having a discussion along that lines at the end, but since you brought it up, I think it's maybe a good question to ask right now. So okay, so far I've described in some details of what an RNN is, and this is really kind of even though there are more variants and they do things in a slightly different way, but at a very high level, this is really all that an RNN is. Given this, I have two questions. One is my description clear enough? And two, if it is clear enough, what is the expressive power of an RNN, right? Okay, so maybe I should do one thing. I should, before asking that question, I should make one aspect of this bit clearer, and then I maybe ask that question once more. It'll also give you some time to think about it, I guess. So far I've been saying things like, oh, pass in this xi, pass in this y, whatever they are quote unquote, right? And pass in these states. But the question is, what are they, right? So since this is a neural network and these are really input neurons and these are output neurons, and when I've drawn this, what I really mean is that there is actually, all the connections that you would expect out of a normal neural network here, right? So these really xi's and yi's can really only be vectors in Rn, right? So xi is going to be in some Rn, yi is going to be um, in some Rm, and si minus 1, all of these guys, they're going to be again in some R, let's say ns or something like that, right? So all of these are going to ultimately be some vectors. So at the end of the day, whatever we have, this RNN architecture, it's actually going to take in something from a set that looks like. So it's going to take in a word where each element of your word is a vector in RN, and it's going to give you back a word where again each element or a sequence where each element is something inside RN, right? And this is okay for us because really going from vectors to something more complicated or something more specific is something that we have seen so far, right? So for example, if you want to actually do text completion, you can. So let's say that you want to do text completion and you're only interested in English, right? So then your RN, so like what your input is really is just a list of characters, right? So let's say you have TH, and then you want the network to complete it, right? Or let's say THR, and you want the network to complete it. So each of these guys is going to belong to some alphabet sigma, which is, let's say, all your capitals, all your smalls, um, and let's say comma, full stop, something of this nature, right? What you can do is you can convert this into a vector in the most naive way, where you have, so let's say that this sigma is of some size, you convert it into a vector of r size of sigma, where this is a huge vector, and each component of this guy is going to be 0 except for the particular thing that you're seeing. So if I want to convert t, for example, there will be some position here which encodes a small t, that will be 1, and everything else will just be 0, right? So this is known as a one-hot encoding. And if you have something like, if you want to process things like sequences of characters, you can always do this. Similarly, the output that you will get out of RM, you can always again interpret that as a bunch of scores, right? So let's say that M is also your size of your sigma, and since we're doing text completion, right? You've set up the network in such a way that M is also this size. And then you're getting a bunch of scores, right? So some 0.5, 0.2, etc., etc. And each of them again corresponds to each possible character that you can put in that particular place when you complete things, right? So then what you can interpret this is that the network is telling you, okay, I'm going to give a score of 0.5 to the event that A is a good next character to put. I'm going to give a score of 0.2 to the event that B is a good next character to put. And maybe it ends up giving a score of 20, some very high score, to O being the next character to put, right? So then you can interpret as this that the network is really telling you that since the maximum score is in O, the network is really just asking you to choose O as the next character to put in, right? So when I'm saying that this guy takes in inputs of sequences of, let's say, letters or whatever, I'm actually converting the input sequence to a sequence of vectors for something like text, or a language from a finite where where characters are coming from a finite alphabet. The most common way of doing it is via things like one hot encoding. In natural language processing, people have often done text completion where each element is not just characters but rather things called tokens, which are combinations of multiple characters, and they have very interesting ways of converting these tokens into vectors, which I'm not going to go into, right? But I'm just saying that this is something that can be done. And similarly, if you have things like let's say an audio signal, then really it's just R star, right? Because each at each time point your signal is going to be some real value, right? So this also you can convert. Similarly, if you want to process video, then each frame is an image, and we have already seen how to convert image into a vector into Rn, right? So that's again some Rn star, right? And similarly, you can always interpret the output as being whatever conversion you're doing with some kind of a score, right? So if we are converting characters into one hot vectors, the output is also talking about characters, but instead of saying which character choose, it's going to give you some score, and then you pick one which has the highest score, or you convert your scores into some probability distribution. You pick one based on sampling that distribution and so on, right? So all of these kinds of things can be done. So just to concretize this, right? So when I'm let's say I'm going to complete, I'm looking for a completion of THR. What it's going to look like is I have um, let's say this guy is going to be my T, and then I'm going to do some kind of encoding. Let's say the one hot encoding I described previously, and I'm going to get this guy. I'm going to pass it to the network. The network has seen some hidden state already, right? So this state vector S is often called the hidden state, and then it's going to give me some output. So I don't even really care about the output initially. I only care about the output once it sees the whole thing. So let's forget about this one. And then let's say it sees H. I again convert it into some vector, and again the network sees the hidden state from the previous step and then converts it to again some output, and again it sees R, and again it converts it and produces some output and so on, right? So this output finally is what I'm going to interpret as my network telling me how I should complete THR. So I'm going to take this output. This is going to be a vector of various scores, and I'm going to look at where the maximum score is lying. Let's say it's lying over here, and I'm going to look at what character that particular position corresponds to. Let's say it's an O. So I'm going to think, okay, the network says that I should actually complete this with an O, right? And that makes sense because THR, if you complete with an O, you're slowly building up the word through, right? So yeah, so this is how these networks work. Now, given this, let's say that I'm doing this one hot encoding, right? So let's say that my input character belongs to some sigma, and I'm going to do a one hot encoding, and then I'm going to pass it to the network, right, in this kind of a manner. And then I'm ignoring every output except for the final output. So I pass it to the RNN, and I look at the last output, and let's say that my output has got only it's a vector of size 2, and I look at, okay, is the 0th element the highest one, or is the 1th element the highest one? If the 1th element is the highest one, I say that the network is giving me the output 1. Otherwise, I say that it is giving me the output 0, right? So if I do a setup like this, I can actually take something from sigma star and return 0 or 1, which is precisely what a machine identifying a language from sigma star, you know, should do. So in some sense, neural networks are some kind of a machine that can identify some class of languages from sigma star, right? So my question is now, what is that class of languages? Is it, what is the expressive power of an RNN in some sense, is my question. So is the question clear? Is what an RNN clear? Do you have any questions, and what is the answer to my question? Yeah. So any guesses? I mean, just even wild guesses are okay.
Any guesses?
Are you guys there? Anything in the chat?
Was the question why are they not successful?
No. So I'm not actually even asking that question, because I mean, then you have to define what you mean by successful, right? And I'll discuss that to a certain extent. But my question is, what is the expressive power? Like, so I can identify some class of languages within neural network, within a recursive neural
So
network,
when you
or a
ask what is
current
the
language.
expressive part, to be more precise, what kinds of languages can RNN accept?
Exactly. Yeah.
That is your question, correct? Yeah.
That is my question. Yeah. Yeah.
If it has loops and if it can do conditions, I guess it's Turing complete.
No, it's not. So I'll tell you why. See, one of the things that you'll need to make something Turing complete is you need a tape, and the tape has to be able to have arbitrary length, right? So typically in a Turing machine, when a Turing machine operates, what's happening is that you've got this arbitrarily long tape, right? I mean, we say infinite tape, but really it's just a tape that can be arbitrarily long, and it's going to read something from the tape and then do some simple, quote unquote, simple processing using just a finite state machine, right? And then it's going to write something to the tape. The idea is that it can store arbitrary amounts of information within the tape. This is really what gives Turing machines their expressive power, right? I'm claiming no, it's not, because that there is no tape here that can store arbitrary amount of information. Remember that all this guy, so when I'm creating the completion, or when I'm, let's say, uh, accepting it or rejecting it at the end, all that this guy is seeing, see, if the final accept or reject is going to be produced by the last iteration, right? So let's say that it's going to look something like it sees character 0, character 1, character 2. Let's say my word was 3 characters long, and then this guy is finally going to say be this kind of a vector with a score for 0 and a score for 1, right? So this guy is finally giving me the signal whether I reject or accept, right? Now this guy is being produced by this particular network, and all that this particular network sees is the current character and the previous hidden state. The previous hidden state is just some vector in some RNS, right? So if you are going to claim that this is as powerful as a Turing machine, this vector in RNS is somehow has to encode arbitrary amounts of information, right?
History.
Yeah, arbitrary amounts of history. So is that the case? I mean,
So it's just single state that keeps getting updated every
Yeah.
time.
yeah, yeah.
So it has
So I'm going
finite
to
memory.
claim, yeah. So I'm going to make a claim, and I'm not going to prove it here. So if you want a proof, we can maybe discuss some other time. But it is exactly the RNNs have exactly the expressive power of a finite automata. They don't do anything more than that, right? They can't do anything more than that. So if you want to look at it purely from a formal language theory point of view, ultimately you're doing a lot to finally just get a finite automaton, right? But that's at one level that's fine. Of course, we now know that there are far better architectures than RNNs and LSTMs because transformers are there, and transformers are actually more expressive than RNNs and LSTMs, which means verifying them is also harder. But anyway, maybe that's a discussion for a separate day. But because these RNNs can only store finite amounts of memory, they can't do anything that a finite automata can't do, right? So in some sense, based on what your RN vector is, like the Bruce sketch is going to go like this, based on what your RN vector is, the neural network that sees things, right? So the neural network is going to see some state vector over here, right? Si. Based on what the state vector is, finally only so much can change in the intermediate layer in terms of which neuron is active and which neuron is inactive, right? That can be an exponential amount of possible changes, but it's only a finite number of things, right? So ultimately, this state vector can really only affect the network in a way that creates finitely many possible choices, right? So this is then ultimately nothing more expressive than a finite automaton. It's exactly the similar case as if you have a program where your loop is only really reading to and writing from a finite set of variables which take finite amount of memory on your RAM. You can always model that as a finite automaton, right? It might be a very complicated one, and that might mean that formal analysis of that program can still be very difficult. This doesn't really give us immediately something big, but you can, I mean, always model it as a finite automaton, right? So yeah, so this is kind of the point, is that you can never really do something that a finite automata won't be able to do. But then remember that what we really are interested in machine learning typically is not to be able to do something 100% of the time, but to be able to do something that we find very hard to define with some reasonable amount of accuracy, right? So from that perspective, maybe this is good enough, is what people to think. Of course, when people were coming up and experimenting with iron, they knew very well this is just a finite automaton. But they were like, okay, maybe still this can do text completion in a meaningful way. Maybe it can still look at an audio signal and determine whether it's identify the voice in the audio profile reasonably well, right? I mean, there is nothing to say that a finite automata itself won't be able to do that. So maybe this is a way to get to something that is essentially just a finite automata, but we've coded up in a very different way that can actually do this. So yeah, so the expressive power doesn't really tell us much about the performance. There's other aspects to why they underperform.
Yeah, there is a question,
But yeah,
Diganta besides Sasank,
correct.
yeah, on the chat.
Yeah, so how do I reconcile with this the fact of the universal approximation theorem, right? So what does the universal approximation theorem tell us? The universal approximation theorem tells us that a neural network, this is a very good question. So a neural network is given a function f. I'm going to give the precise statement of this theorem, right? So given a function f from Rn to, actually the original versions only deal with Rn to R, but you can easily generalize it to some Rn, right? Given any f that has got some nice property, so let's just say that f is continuous and some other kinds of nice properties, there is always a neural network n f that approximates f close enough, right? So for all f and for all epsilon, there exists a neural network nf, so that nf x minus fx is always less than epsilon, right? So this is essentially what, and there are various versions of this theorem depending upon what you mean by continuous and how big of a network are you interested in, and so on and so forth, right? But all of these universal approximation theorems, this is the crux of the statement. Notice here that I've not said anything about a sequence here, right? So let's try and apply the universal approximation theorem to this setting and see what happens. See here, what is my function f, right? Or here, what is my network n? The network n takes in a couple of things. It takes in x and the hidden state, right? So this is going to be in some Rn plus. So when I say plus, I mean like, concatenate, let's say, right? Rns. And this is again some, some big Rn plus ns kind of thing, right? So it takes in some huge thing over there, and then, but then ultimately it's just a vector, and it outputs something in Rm plus Rns again, right? So what universal approximation theorem tells us, that if I have any f that takes in x and s and gives me back a y and an s, I can always approximate this up to any degree of approximation, right? But the question is the f is having an f that just does this, is that itself expressive enough? If I somehow give you like a god-given f, even then, can I always accept or reject any class of languages by just having a system that takes in x0, x1, x2 and some s0 and applies this same f over and over again, right? It produces, let's say, y0 and s1, and again I apply the same f, y1, s2, f, y2, and so on, right? So even if this f was not a neural network, let's just imagine this f is some really complicated function, like some god-given amazing function, right? Even then, ultimately, the issue is that this f, when I finally want to accept or reject, which means when I'm looking at the last invocation of this f, which is going to tell me 0 or 1 inside this y2, let's say, this invocation of the f only gets to see the last character and the last state. And remember, no matter how beautifully amazing your f is, this last state is ultimately only going to be,
Yeah,
something
but
that is inside my
but
RNS.
here is a slight twist or tweak to your approximation function that I would make to see if it thing. Let's suppose that you restrict. Now here, of course, I restrict the bound. Okay, and say, oh, can I mean, I restrict the bound of the sequences, okay, up to a certain maximum, okay,
Hmm.
and then ask the question if I could approximate
Hmm.
what the possible completions are for all sentences for up to that bound, up to a
Right.
certain amount of accuracy. Okay, that you should
Right.
be able to do, no? Because
Yeah, that you should be able
then
to do.
now you can have the context. You could, for example, say the output of every node in your neural network, including the output.
Yeah, you just need to have a
Okay.
big enough S context to capture all of
Yeah,
the
but of
history of
course
bigger
that
problem.
I'm also bounding the number of in the length of the input sequences. Okay,
Right.
if you bound the
Right.
number of the length of the input sequences, and if your alphabet is finite, then you
Right.
only have a finite number of the history will also be finite, bounded. Okay,
Right.
for a
Right.
particular that thing. Then my question is, if you should be, with making F, choosing appropriate F. And if you have large enough context, you should be able to come ever closer to getting the function that processes sequences ever so accurate, no? For a bounded.
Yes, yes, absolutely, absolutely. So in some sense, if I am only interested in languages in sigma to the n instead of sigma to the star,
Ah,
right?
correct.
So I'm
Yeah.
saying words are only up to length,
Yes,
some
that's
capital N, let's say.
precisely. Yeah, I mean, that's my formulation. Yes, correct. Yeah.
Yeah. So then again, we should be able to do we should be able to identify or classify any language using a suitable F. And if we are able to do that using a suitable F, then we should be able to find a suitable NF which can do that, right? So then basically in this class, RNNs can do anything in some sense, right?
Hello, sir.
Because then, yeah,
Yeah.
yeah.
Was there a
Yeah, like,
question?
yeah. So, can you repeat the universal approximation theorem once again? Like, what is the assumption of the function? Like, if we want to say like there are input outputs, so like there might be many functions that have same input outputs. The like, if we want to define a function, we for every possible input of the domain, we need to define every possible output, right? So, uh, like, it's kind of saying that we're already approximating the function before we giving it to the neural net. Like, neural net doesn't know if it's kind of like which function it is, but on the based on the inputs we have already given, like say we have defined 5 pairs of input output, then like given that function, like neural network will try to approximate that. For the function to be Turing complete, we need to like define for every possible input, we need every possible output, then might be infinite. So that might be the reason it's not applicable to universal
Yeah,
approximation
yeah, yeah,
theorem.
exactly. You're right. So it basically comes. So I've sort of hidden that detail away when I was writing the statement here, where I'm saying continuous dot dot dot, right? So there are various versions of the universal approximation theorem, which puts various kinds of restriction on what your function f is, but almost all of them have some, they say that the function needs to at least be continuous. Some of them say that, okay, if you are continuous and differentiable, we can maybe have a smaller and basically you can do various kinds of bounds changing using various different classes of functions, right? But most versions of the universal approximation theorem will say, and the original classical version just says f is continuous. That's all they need, right? But immediately when I say f is continuous, I am in some sense, restricting myself in the amount of information I can pack, or the amount of information I can unpack from the state space, right? So that is the kind of point that I'm saying. So so like if I am saying that f is continuous, then I cannot in some sense unpack arbitrary amounts of information from this state space, right? Because I mean, another thing that I should say is maybe that this uh, uh, typically these state vectors are also bounded, so you want this to be bounded as well.
Yeah.
So
Diganta, so it's
yeah,
7:18. So
correct. I think this is a
yes.
good discussion, but maybe let's
Yeah,
move
I
on.
think we could revisit this. Okay, so this is
Yeah, yeah,
it's more theoretical discussion, but it's very interesting. So I think you should take the rest of the time. So I should without actually getting into dinner time. So 7:30 is the I'm sorry, 7:30 here. Okay, which is already probably past your dinner time. I'm sorry for that. Maybe you can use about 10 minutes or so to finish up the
yeah,
rest.
yeah,
Yeah, yeah.
yeah. So let me fairly quickly do that.
Yeah, we could revisit this, okay,
Correct.
at a later
So
time about this capability. I mean, the limits of expressive power. Yeah, yeah.
right. So okay. So I'm just going to skip over most of the slides. There's various types of RNNs, but I think maybe details of what an LSTM is something that, interest of time, unfortunately, I didn't like pace myself well, I guess. But like the details of what an LSTM is, I'll just skip for the interest of time. But what I want to say is that it is a kind of RNN. So it's like there are more things happening inside an LSTM, but ultimately the picture that I have is still accurate, right? So, in some sense, if you imagine a normal RNN, everything is connected to everything, so you can have all possible interactions. What LSTM does is that it tries to say that no, I'll only have certain kinds of interactions motivated by some concepts of long-term memory, short-term memory, and so on and so forth, right? And that seems to work well for certain kinds of reasons. that being said, let me just quickly talk about some of the details of training, and that will bring up more points about the limitations, right? So how do you train this? I mean, we have talked about training a neural network. In some sense, the typical way that we do is we have input and output pairs, and then we say that, okay, I'll calculate the output of the network compared with the actual known output that I have for this input, and I'll somehow take this distance. This is going to be my loss function. And then since the network is going to be parameterized by weights and biases, this is just a function of those weights and biases, which I then minimize, right? So then I minimize this L. I find a value of theta that minimizes the L via gradient descent and so on and so forth, right? So it's about setting up an optimization problem. So how do you set up an optimization problem over here, right? So ultimately, typically for training RNNs, we'll also have some data sets where we'll have words, right? So we'll have sequences of xis, and I want and this data set will say that, okay, for this sequence my neural network should produce a particular kind of sequence yi, right? So then I can do the same thing, but I'll have to run the whole network on xi and then compare against all of the yi's. And this is what you do. You do this by unrolling, and it's also often called backpropagation through time, where what you do is you take, let's say that my xi has got, again, three things, just following this diagram, right? So xi has got x0, x1, x2, and I'm expecting y0, y1, y2, right? So then I get o0, o1, o2 over here. So what I say that, okay, y0 should be close to o0, and y1 should be close to o1, and y2 should be close to o2, right? So then my loss function basically becomes something like this. And of course, I mean, O0, O1, O2 are outputs of the network. So that whole thing has got the whole expression of the network built into it, right? So really what I'm saying is my loss function ends up looking something like, okay, Y0 should be close to take the network, take X 0 and S0 given theta, right? And y1 should be close to, okay, take the network, take s1, and again remember s0 is again the output of the previous application of the network, right? So I'll nest it in here. Okay, take s0, x0, s0 given theta, whole thing given theta, right? And then so on and so forth. So every time I'll have to, when I have this loss function, I have this ever increasing deeper nestings of this n going on, simply because I have to kind of take into account the fact that this guy that is being passed from the previous thing was actually produced by a previous application of the network, right? So to keep on doing this kind of nesting, and that means that ultimately your L is going to be this expression where you have terms of this form, right? Bunch of nestings of n. And this is a big problem. This is a problem because the behavior of this guy with respect to gradients is not nice at all, right? So to understand that, let's just forget about the fact that n is a network for a second. Let's just imagine that my network is given by a single weight matrix. So what I'm doing is I have got some big weight matrix W, and then I take in a vector that has got X and S concatenated, and then whatever it produces, I'm interpreting it as a vector with Y and S concatenated, right? So then some kind of a, this kind of nested application of N is going to look something like, take W and multiply it with itself a bunch of times, which is basically some W raised to the big power N, right? Now, when I'm doing gradient descent, what is it? I want to calculate the gradient, right? Which is given some fixed input and so on. If I change one, component of this matrix, how much does the output change, right? If I'm already multiplying this matrix by itself so many different number of times, very tiny change in this is going to create huge changes in the output, right? And this becomes very difficult for gradient descent to handle. Basically, what happens is a number of your gradients will just simply go to zero. A number of your gradients will just blow up, and then gradient descent runs into numerical issues, and training just kind of stops, right? So this is, so this is a numerical issue, but it is indicative of an information issue. See, all of these gradients, when we're doing these multiple applications, all of these gradients are trying to simulate what would happen if I were to change the behavior of the network on the whole world, right? So it's simulating how the network would encode the information in the state at each point, which we've already discussed is a difficult problem. There's only so much you can pack into the state vector. And now you're, saying that, okay, I'm going to remember everything that happened a long time back, and I'm going to always be able to change with respect to that. That is never going to, that doesn't happen, right? So this gradient, when I do this kind of application, basically just says that, okay, if I were to make a slight change in the network, how does the network, or how does or what the network remembers from the first character, how does that change, right? Well, it's we have already seen that from a formal language point of view, it's not even clear that the network will remember anything from the first character, right? Given a long enough sequence. At some point, it has to forget. And if at some point it has to forget, this gradient will not, it cannot always reliably capture the meaningful information, right? And the way that this shows up numerically is that the gradients blow up or the gradients go to zero. In most cases, it turns out that the way that people set things up, the gradients end up going to zero. So this is, so this is a problem. And what it shows up as, if you try to train something, is the gradients blowing up and the gradients saturate, the gradients going to zero, and so on. So this is something that is indicative or symptomatic of the more deeper problem that really RNNs and all architectures based on RNNs, LSTMs were built to somehow sort of alleviate this issue, and they do alleviate this issue, but it's not a fundamental change. It is in some sense just a workaround, an alleviation, right?
Yeah.
So this is something that just happens, right? And that is where transformers come into the picture, and they're much better, and so on and so forth. But yeah, this is all I wanted to say.
Yeah, I think this is a good point to stop. Okay. And maybe when we revisit, LLM models and or transfer models, let's see how we structure the rest of things. We could, I have the general question now, how does transformer models or, the language models avoid this, overcome or circumvent to whatever
Yeah.
extent that they do this training issue. The
Right.
training complexity, but we can revisit at that time. So I'm hoping that at least you've got a good overview of what RNN is and what the challenges of expressibility as well as training is, and that's what the key takeaway from this session ought to be for you. Okay, so starting next week, it'll be physical classes because I'll be back. So we'll have to figure out the time slots for that. That'll be done. I will be communicated to you and through email and other means. So that's what I wanted to let you know. And yeah, we will continue the RNN verification topic for next week. Okay. Uh, yeah, unless you have some very immediate specific questions for Diganta, we will adjourn. So do you have any questions? Okay. And thank you, Diganta, for
Yeah. Thanks a lot.
putting
Also,
in.
thanks for the very interesting questions.
Okay.
I hope that I was able to do them justice, and so on and so forth. But yeah,
Yeah, full justice. Full
will
because the
take a
topic is a
much
fairly
longer.
big
Yeah.
one, and that's why I said that
Yeah.
revisit it when we give overview of LLMs. Yeah,
Yeah.
we
Yeah.
can
Yeah.
certainly do later on. Yes.
Yeah. Yeah.
Okay. Thank you.
Thank you.
Thanks. Thanks. Sorry, is there a question or
Oh, yeah.
somebody was
That's
saying
okay. Was there a question? No, I think he was just.
No, no. I think they were just. No, no. Is there a question? Sorry, I think I saw it.